start there. Yeah, Peyton.
Can you use 16?
Sure. I'm just going to use the technology to get the graph assigned, if that's okay with you. All right. So the question here asks to make a careful sketch of the graph of f, and then sketch the graph of f prime on the same axis, and see if we can guess the formula for f prime based on what we're seeing. So first thing I'm going to do is I'm going to go in and put in all the places where the derivative is 0. So everywhere where I have like a horizontal tangent, I'll go ahead and do that. So far so good. And then if I look here, it looks like the slope there is probably +1. So I'll plot that point. And then like the slope there looks like maybe -1. So plot that. And so on and so forth. That feel okay with what we're doing so far? And that's probably enough. Do you recognize that graph? It's cosine, yeah. So your dead giveaway is that 0, 1. And you could do a little bit of checking to make sure, but the zeros are in the right place, the max and mins are in the right place. Almost assuredly it's cosine. Cool, Peyton?
Mm-hmm. Thank you.
Sure. So again, there's nothing sneaky that we're doing there. We just kind of sketching the derivative using the same method we kind of talked about during the lesson of finding the places where the slope is 0, putting those in first, and then like finding some intermediate points and estimating the slope in there and plotting some points. You know, really kind of the trick was identifying those places where the slope looks identifiably like a number that you can eyeball, but looks really close to 1 and -1 in those spots, and it is. Now I have the benefit of like knowing what's going to happen, so it looks really easy and obvious when I do it. But that would have been the hitch there. Others from 2.8, or earlier, I suppose. No, there's nothing. We already turned in like 2.1 and 2.7 and took questions on that stuff last time. But if more stuff's come up, we can certainly talk about that stuff too. Kylie.
Can you do 29, please?
Sure. 29 on 2.8?
Yeah.
Okay. Let's make sure I'm on this. Sir, and God bless you. You're welcome. Yeah. So it asks us to find the first derivative and then state the domain of both the function and its derivative. And we're looking at number 29, right? Okay. We'll figure that out for right now. All right. So g prime of t is going to be equal to the limit as h goes to 0 of 1 minus 2 times t plus h over 3 plus t plus h minus 1 minus 2t over 3 plus t all over h. So far so good, Kylie? Okay. So quick check, if I plug 0 in for h, it's 0 over 0, so it's indeterminate, so I have to do something to kind of clear that hurdle. In the case where I have a like complex fraction like this, where I have like fractions on top of fractions, typically the easiest simplification technique you can use is to multiply the top and bottom of the big fraction by the least common multiple of the denominators from the little fractions. So my denominators are 3 plus t plus h, 3 plus t, and then 1, good for h over 1. So far so good? So 3 plus t plus h and 3 plus t are relatively primed. I can't like decompose those into factors of each other. So my least common multiple is just going to be the product of those two. So my go-to, oh my gosh, that's so big. So we're just going to multiply the top and bottom by this. Still good so far? So that's going to distribute. It's going to go to, oops. It's going to go here, and then it's going to go there. When I multiply to the little fraction, the 3 plus t plus h's are going to cancel. And I'm going to be left with 1 minus 2 times t plus h times 3 plus t. So far, so good. And when I multiply to the little fraction, the 3 plus t's are going to cancel. So I'm going to have 1 minus t times 3 plus t plus h. And that's now going to be left all over 3 times, or h times 3 plus t plus h times 3 plus t. And I've knocked out the complex fraction part, right? Great. What I'm going to do now is I'm going to FOIL out the numerators and then look to combine like terms. So this one I'm going to think about I'm going to distribute the 2 through there. Is that okay? So we go and we FOIL. We're going to have 1 times 3, and then 1 times t, and then negative 2 times 3, and negative 2t times t, and then negative 2h times 3, and then negative 2h times t. right? And then we'll have 1 times 3 and then make that negative, 1 times t and make that negative, 1 times h and make that negative, negative 2 times, or negative 2t times 3 and then make that the negative, so I have positive, negative 2t times t and then make it, or apply the negative, so I have that, and negative 2t times h and then make it negative, so I have that. Yuck Aruskis. But I'm just kind of like foiling the stuff out. And now let's look to cancel. So I'm left with 6h minus h, it looks like.
Wouldn't that be minus 6h?
I'm sorry, what?
Minus 6h? Minus h or no?
Minus 6h minus h. Yeah, what did I say the wrong thing?
You said 6h.
Oh, yes, thank you. Yeah. Minus is still there. Reduce those guys out. I'll just call that negative 7a. And when I do the limit, those h's go to 0. So I backed. So good? It's a lot of algebra there, but it's okay. The domain here is going to be everything except for negative 3. Right? Since it's a rational function, I only have to worry about where the denominator is 0. That can only happen when t is negative 3. If I go back to the original, it asks us to do the same thing for this. So, didn't lose any domain apparently on this one, taking the derivative, right? That would tell me that this function is differentiable across its domain, since the domain of f and the domain of f prime are the same. That I can do the derivative at every value that I can plug in for f. Does that feel good?
Can you repeat how you said it's differential?
Yeah, so since the domain of f and the domain of f prime are the same, that means every value I can plug into f, I can plug the same value into f prime. So that means the derivative exists for every value that I can plug into f. And that's the definition of differentiable, is that if I can plug, if the derivative gives me a finite value back, it means it's differentiable. Since I can do that for everything in f, I can plug into f prime and then I have differentiability everywhere across its domain. Right? Negative 3 is not differentiable, but you can't do that at f anymore. So we're differentiable across our domain. Does that make sense? Yeah, for sure. Clarify the vocab's important. Like what that stuff means is important. For sure. Like talk it through if you need to. Like happy to do that. Like understanding like if you're given a problem and they say it's differentiable, like what the heck does that mean? What can I do with that? What does that say? How else could I write that symbolically? Like that's exactly what we want to be thinking about. Like how do I use this definition in a problem, or what would I need to show in a problem to draw that conclusion? That's exactly the kind of thinking we want to be driving towards. Last call on 2.8. Is there anything else you want to talk about? These I think were pretty good choices, guys. The two main skills would have been like, can I go from the graph of f to a sketch of the graph of f prime. I think that's a 100% a worthwhile skill to have, like what Peyton asked about in the first question. And then the other real skill is, can I find that general derivative using the definition of a derivative, which is the question Kylie asked about, and we can relate that to what can we say about the differentiability of the function by looking at the domains of f and f prime. I think that covers like the main ideas from 2.8. So these are a good couple of questions to ask about. Alice, do I need to move this up? Looks like you're still like furiously writing. I didn't mean to. I just got excited about like getting the result and saving like the point of the problem was to notice this. Again, this process we used to take the derivative of this. It's rough, right? That's a lot of algebra, a lot of stuff to keep track of. Very easy to like drop a negative sign or to forget to FOIL one of those terms out. We improve this derivative process in the coming chapter and start looking at shortcuts on ways of avoiding having to do this limit definition. As you see, the more complicated the function's getting, sometimes this gets really pretty nasty. So that's going to be, we're going to start doing that in 3.1. It's like getting around having to do this process every single time. And that's really the crux of chapter 3 is like, what are all the little derivative shortcuts we can build out that we can use to take advantage of doing things the hard way. All right. 2.8 homework quiz time. You guys asked some good ones because I think they're pretty relevant to what I'm going to ask you to do. They're easier than what we did here. Like the algebra is much nicer. Again,
Then you put a bunch of square roots and you put a bunch of cubes in there?
no, there's no cubes.
Oh my god.
Yeah, there's no cubes.
No e's either?
No e's on this.
There we go.
Like those limit rules and stuff, yeah. Or the exponential rules. Are nasty to kind of wiggle your way through on the limit stuff. And we haven't really talked about indeterminate numbers where you have like, 1 to the infinity or something, and how to like our way through those.
Oh god.
It's gonna be like relatively easy looking. Like,
This is what I did with Mario yesterday.
yeah, perfect. Perfect. Math with Mario.
So I did that.
Why is that?
Again, like, you can use a calculator. I don't know if it'll be really much help to you on this. To be honest with you, it's mostly like symbol pushing, but if it makes you feel better to have it, and you're like, I'm going to use it to do something, it's like, okay, no problem. No complaints from Mr. Bullock. You're welcome. You're welcome. You're welcome. Last but not least. So on number 1, notice I gave you the definition of the derivative there. You just have to use it. And needless to say, on number 2, there's like infinitely many answers, right? There's not like a specific thing I'm looking for. You know, we draw it almost any way as long as it meets the criteria that I'm given. Set it there, Anthony. Thanks. Thank you. So you haven't written this out. What you wrote was f of x parentheses plus h, not f of parentheses x plus h. See? So this part is not correct, and that's why it's like it doesn't look right and it's not working. Okay. So it's going to be a function in terms of that, so I think it's f of x plus h. So 0 before it should be. Yeah, good call. Right. I just need the picture. I just want the graph. Depending on what people went with, it would be completely unrealistic to come up with an equation. So, all I need was a picture. Couple more minutes to finish up those couple that are still working. It continues everywhere. The function f has to be continuous, or not different. So that'd be a feature that would occur as this whole make it not different. That would be acceptable. Yep. The directions don't state that it has to be in a specific form until form is found. On a test quiz, I would accept that. With the same, if given the same directions, would accept that answer. All right, ladies and gentlemen, this is the moment you guys have been waiting for. We're going to put to bed the limit definition of a derivative. We're going to replace it with a bunch of shortcuts Here's the downside. Many derivatives you're going to be able to do in your head with almost minimal work shown. The catch is, now we got stuff to memorize. It's a good trade, trust me. It'll turn a problem that would take like a whole sheet of paper to do, potentially into a problem you can do in your head. Yeah. So first piece, the derivative of a constant is 0. Should you memorize that? Yes. Okay, so the derivative of 5, 0. Derivative of 10, 0. Derivative of half, 0. Derivative of e, 0. Derivative of e squared, 0. Derivative of pi, 0. Derivative of natural log of 10, 0. Derivative of cosine 12, 0. Right? You guys get the idea here? Like, we can write a constant a lot of different ways and it can look really funny and scary looking. They're all just 0 when you take the derivative of them. The proof of that, I mean, if f of x is just c, if I apply the definition of derivative, I just have c minus c on top. So it's 0 over h, which is just 0, and the limit of 0 is 0, and we're done. Super easy. Next one, the derivative of x is just 1. Well, the proof of that there's my limit definition. So it's 1. Woo! What's that?
Like, you know how c was the constant?
Hmm?
What is that? Just
So it is the variable x. The derivative of the variable x is 1. But here, the derivative of x to the n times x to the n minus 1. So the derivative of x to the 5th is 5x to the 4th. The derivative of x to the 10th is 10x to the 9th. The derivative of x to the 23rd is 23x to the 22nd. Does everybody feel good about that? Like, think about how much of a nightmare it would be taking the derivative of x to the 23rd. Using the limit definition, we have to FOIL, like do a binomial expansion to the 23rd power. Oh my God. It makes me like, I don't throw up in my mouth thinking about the prospect of having to do that. Right? Like, no thank you. Let's look at the proof of this. The proof here is a little less trivial than the previous two. Right, so this is my initial setup. Very good. Guess what I'm going to have to do here to do the proof? The binomial expansion, really, because it's more than 2 terms that I'm pulling out. There's n of those things. Oh boy. It's okay, good things happen. So the binomial expansion, like nc0, x to the n, h to the 0, plus nc1, x to the n minus 1, h to the first, plus nc2, x to the n minus 2, h to the second, plus c n minus 1, x to the first, h to the n minus 1, plus ncn, x to the 0, h to the n, and then I have minus that x to the n. There. So that's the binomial expansion. Do you need to have that memorized?
No.
No. Not necessary, but you should do. NC0, do you remember what that is? It's 1, right? How many different ways can you make a set of, from a set of n objects, a set with 0 things in it? Just one way, it's like the empty set. Right, remember that's what those C's are, they're like combinations. So, minus n or x dn and plus x dn. Pretty good there? Because, oh, well, I guess it's worth saying that like h to the 0 is 1, right? Everybody's good? Okay. If I look, everything else that's left all has an h in it. You guys see that? So I can take like an h out, and I'd have like nc1 x to the n minus 1 plus nc2 x to the n minus 2 h to the first dot 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 plus nc n minus 1 x times h to the n minus 2 plus ncn. I'm not going to bother with x to the 0, that's just 1, right? H to the n minus 1. That's like all, can just like factor an h out of all that. Boop, boop. And what do you notice here? The stuff that's left all has h's, right? So when I do my direct substitution, what's going to happen to all that stuff?
Zeros out.
Zeros out. And I'm left with, like, all this stuff just kind of zeroes out when I do my direct substitution. And NC1 is just N. Right? Because it's like, from a set of n things, how many different sets can I make that contain one object? Well, there's n of them, right? And you take the first object, and the second object, and the third object. There just could be one thing in there. So that's the, would I ask you to repeat that on a test or a quiz? No. Showing it to you because people in the room, going to take many years of calculus as a college student, get used to seeing proof and being able to write proof, not an expectation for this course, but the exposure I think is beneficial. So I want to just put it out there like that's what it's going to look like. So you build up some intuition for later on in your future mathematics courses of like, okay, like I remember doing this kind of stuff. I've seen this before. It's like the same kind of argument. I'm just going to kind of expose you to it and move on. Should you memorize this?
Yes.
Oh yeah. Oh yeah. How helpful is that? Like mega helpful, right? All right. So this is basically just what we did. I did a bunch of these out loud where we just use that power rule. So I'm not going to do that again. Now notice before, it said positive integer, but that's updated now. It's like, why is it on there twice? Well, it's actually two different rules. Now this second rule covers the first one because a positive integer is a real number, but any real number. So for example, if I want to do the derivative of 1 over x squared, I'm going to want to rewrite this so that it looks like x to the n. How can I rewrite 1 over x squared? X to the negative 2, right? So if I do the derivative of that, I'm going to get negative 2x to the negative 3. Right? Or you could rewrite that way. Either answer is fine. You just asking something?
No.
Are you sure?
Yeah.
Okay. If you change your mind, like chime in and interrupt. It's okay. How nice is this, right? What about the cube root of x squared? How can I rewrite that as like x to the n?
X to the 2
X to the 2/3. Perfect. So when I take the derivative then, I would say it's 2/3 x to the negative 1/3. Or you could rewrite it as 2 over 3 cube root x. That's acceptable also.
I'm sorry, it's from.
Nope, that's okay.
Nx to x minus 1 or x plus 1?
It's subtracting 1.
N1.
So on a test for me, will I care which form you write this in? No. On a multiple choice test, which answer is going to be A, B, C, or D?
Either one.
This one. They'd write it in the most standard form with no negative exponents, no fractional exponents, to make sure that you can algebra your way through it. It's like an extra layer. If it's a written, like a free response question, once the calculus part is done, you can stop for me. Like, I don't need you to spend a bunch of time algebraing your way to like the prettiest answer possible. You may run into a college professor that needs you to do that. I don't need you to do that. For this course, we're worried about getting the calculus part down. And if you muck up the algebra afterwards, we're gonna just punt on that for now. The calculus is enough to worry about, right? But if it's a multiple choice question, you better believe that the answers are gonna be like the most simplified versions of the answers, like the prettiest up. We really prettied up the algebra to get rid of like negative exponents and fractional exponents. It looks really wonderful and beautiful. And there's common denominators that are made and like, so keep that in mind. The takeaway here though is a little bit of algebra to start is often really beneficial to make the calculus easy. We're going to get into, as we go through this, adding in more and more rules that you're able to do more and more complicated looking functions. Always, before you start any derivative, take a look at what you're starting with and be like, if I rewrite this in like a little bit different form, can I eliminate having to do like a bunch of complicated calculus rules and make this really simple? Because the answer is very often, yes, I can like do a little bit of algebra in the beginning and take away a whole lot of mess later on. The hard part about that is seeing when you can do it, right? It's just doing enough problems to get enough intuition to where you can look at it and be like, oh, I see the easy way of doing this. Because most of the time there's a nice backdoor to a lot of these problems that makes it way easier. And the AP exam, they're going to give you lots of problems that have like a real fast way to do it and like a really tedious long way to do it. What they're doing, why they like to do that, is it's testing you to see, like if you see those shortcuts, if you're well trained and you can see the shortcuts, because otherwise you're not going to have enough time to finish enough of the questions to score really well. Even if you can do it the long way and the tedious way. You just run out of time to score super well. You know what I'm saying, guys? So it's like another way that they're testing, like, can you see the easy way to do this? Well, what they do is it's getting really hot in there. What they do is they just make the test long enough to where if you don't see the easy way to do it, it's just impractical that you're gonna finish. All right, let's do this one. So it says, find the equations of the tangent line and normal line to the curve x times square root x at the point 1, 1. I'm not gonna graph them afterwards. So tangent line, we know what that is, right? What's normal? When we say a normal line, do you know what that is? So tangent line is like parallel. Normal line is going to be like perpendicular. So the normal line is going to be perpendicular to the tangent line. What do we know about the relationship between slopes that are perpendicular?
They're reverse.
Negative reciprocals. Yes, negative reciprocals. So we'll do the tangent line first, and we'll just take the slope and flip it, and then make it negative and do the normal line right after. It's almost no work at all. The question though is, how do I do this? Because I don't know how to do like the derivative of a function x times another function square root x. I don't know how to do that. So if I write as x times x to the 1/2, that's good, but I still have a function times a function.
This is X, there's a rule for it, though, right?
What's the rule?
Is it 1?
No, I don't know how to do a function times a function. There's no derivative rule that we have to do that. Is there something algebraic I could do here? Anthony? If I multiply x to the first times x to the half, I get x to the 3/2, right? Or 1 1/2. I'm going to write as 3/2. Can I do the derivative of that now, that it's a single x? You betcha! So we'd have that y prime then is what? 3/2 x to the 1/2. Am I going to bother prettying that up? No, because is it part of my final answer? No. So my slope for my tangent line is going to just be y prime of 1. Square root of 1 is 1. 1 times 3/2 is 3/2. So my tangent line is y minus y1 equals m times x minus x1. Right? Because I'm given the point there. And then for my normal line, it's going to be y minus y1 equals negative 2/3 x minus x1. Done. Right? If you want to clean that up, you can clean that up. Get it in slope-intercept form or something. But those are equations with lines. I'm stopping. You know, like, calculus is done. I wrote you the line. Like, unless you tell me that it needs to be in some specific form, like, nuts to that. Like, this is what you get. Deal with it. Everybody okay? Bless you, Alice. Constant multiple rule. Super important. The constant multiple rule of a derivative says that I can just ignore the constant, take the derivative of the variable part, and just multiply the constant back onto the derivative. So if I'm taking the derivative of 3x to the 4th, I can just ignore the 3 and take the derivative of x to the 4th, which is 4x to the 3rd, And then I just multiply the 3 onto that. Like, how nice is this? Like, real nice compared to what we've been doing. It's like, Mr. Kulik, that's like a page to do the limit definition for. I have to do like some terrible binomial expansion to the 4th power, like a 3-layer FOIL, like, no thank you. We did that in our head. Wonderful. How about the derivative of negative x? Well, I'm going to think about the negative sign as like -1 times x. What do I get here? -1 times 1, or just -1. Yeah, we're liking this, right? This is wonderful. It's going to get better. The sum and difference rule. The derivative operation. You can distribute across addition and subtraction. So if I have a polynomial, like x squared plus x plus 1, I should take the derivative of each term individually, just add them all together at the end. Woo! Yeah! So look at this nightmare. Look at that. Think about doing that with the limit definition. I give you 80 minutes to do it. I bet you can't, right? Like, it's going to be a nightmare. Can we do this in our head with the new rules?
Can you scroll up a little bit?
Oh, sorry.
Thank you.
Can we do this in our head with the new rules? You should be able to, if not today, after the homework tomorrow, for sure. So we're just going to take them individually. The derivative of x to the 8th. 8x to the 7th. The derivative of 12x to the 5th. Excellent. 60x to the 4th. Good mental mathing. 4x to the 4th. 16x to the 3rd. Look at you guys go. 10x cubed. 30x squared. 6x. Just 6. Take the negative with it. Derivative of 5. 0. So we're not going to write anything. Look what that, we did it in our head. No work needed to be shown on this. I just looked at it and wrote it down. 80 minutes, 79 minutes later, we're still trying to grind through the limit definition. That was a 30-second problem, at best, right? And that's only because you stalled for a minute. Big 5 times 60 is, or 5 times 12 is, it's still a little early for that kind of mental math. All right. Next example says, find the points on the curve, yada, 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 where the tangent line is horizontal. That means the slope is 0, right? That means that the derivative is 0, right? Everybody's okay? The derivative of the slope is the slope of the function at that x. So what we're going to do, we're going to solve this equation, or find the derivative of this equation, set it equal to 0, solve for x, and then we have to plug the x's back into the original to find the y's to go with them. Everybody okay with that? Who can tell me the derivative? 4x cubed minus 12x. If I set that equal to 0, how are we going to solve that? Factor. Great. What are we going to do?
Take 4x out.
4x out. Then what? Okay, so plus or minus square root of 3. We missed one other answer though. 0. right? If we take the 4x and set it equal to 0, we get 0. We take the x squared minus 3, set it equal to 0, we get plus or minus root 3. Everybody good with the solutions? Okay, these need, it wants points though, so these are my x's. To find my y's, we have to go back to here. So 1 point is 0, 4.
Does that mean they want 4 points?
Will be 3, right? 0, and then 1 for root 3 and 1 for negative root 3. Root 3 to the 4th is 9. Excellent. Root 3 squared is times 6 is plus 9 was 27, and then plus 4 more is 31, I think. Again, you could use a calculator to do this. I'm just, get mental math going. What's the nice part about the negative root 3? Who sees it? What's it going to be? Still 31, right? Because all the negative root 3's are to even power, so it nukes the negative sign anyway. So it's going to be the same answer. What do you guys think? What did we just find? We found the extrema for this polynomial, the mins and maxes, right? How did you do that before, algebraically? Couldn't, right? If I gave you a polynomial and asked you to find the mins and maxes, you were stuck using your calculator and just using the min-max command, right? If I take your calculator and take my hammer and I smash it, you're out of luck. It's like, Mr. Kulik, there's nothing I can do with this. Like, you broke my calculator, I can't do it. That's what you can do now. Be like, Mr. Kulik, sit back, I got this. Just a little bit of algebra now, and tiniest bit of calculus. Is everybody okay? You see what I'm saying though? Right, like what a nice tool this is, that now algebraically we've gone ahead and patched something that we couldn't have done before. All right, physics. The equation of motion of a particle is given by yada yada yada, where s is measured in centimeters and t in seconds. Find the acceleration as a function of time. What is the acceleration after 2 seconds? Okay. Question from yesterday, what's the relationship between position of an object and acceleration? Acceleration is the second derivative of position. So like, you have position, you take the derivative, you get velocity. You have velocity, you take the derivative, and you get acceleration. Everybody okay? So what are we going to do here? Just going to take the second derivative. To take the second derivative, I have to find the first. What's the derivative of 2t cubed? 6t squared. And then 5t squared. 10t. And then 3t. 3. And then 4 is 0. That's the first derivative. The second is going to be derivative of 6t squared. 12t. Derivative of negative 10t. Negative 10. Okay? So a of 2 is just going to be and I guess it's centimeters per second squared. So we know that our unit is centimeters. Taking the derivative adds a per second. Taking the derivative again adds another per second. So that you end up at centimeters per second squared. or centimeters per second, if you wanna write it that way, but like, who wants to write it that way? It's kind of non-standard, but it's not wrong. So you guys remember, maybe, from your pre-calculus course, that we said E was the limit as x goes to 0 of 1 plus 1 over x to the x? You may not remember that. I'm sure you wrote it as, Mr. Myers wrote it on the board at one point and it never came up again, so you didn't remember it. That's fine, that's not a big deal. This is just another kind of alternate definition. I don't know that I've ever seen it come up in a place where it's necessary for you guys. I don't think that's a memorizer, but this one is. The derivative of e to the x is e to the x. What's the second derivative? E to the x. Third derivative, e to the x. Fourth derivative, e to the x. Okay?
How to get around your tricks now.
Got a whole new bag of tricks that we can use. Just as some extra examples. Do you have enough derivative rules to be able to do this derivative? 3x minus x squared over square root x. Yeah, how do I do it?
Then 3x is supposed to be
Since the denominator is a monomial, I can break it into fractions with a common denominator, right? And we know that square root of x is just x to the 1/2. And we divide exponents, they subtract. And now you're in a form where derivative rules apply. Easy peasy, right? Do I have a derivative rule to handle this as it's currently written? No. Can I make that into something I can handle? Yes. What would I do?
Just
Foil it out, right? Yeah, 100%. Now it's easy, right? So these are like some of the most common tricks that I will pull on you for right now, where I'll give you like, oh, I'm gonna, like, give you some fraction, but as a fraction you can decompose into into common, terms with common denominators that you can then simplify down into power rule problem. Or I'll give you something that like, oh, I can boil that out and turn it into, like a polynomial enough problem that I can handle. So the assignment there's on the board, I'll have a delta math related to this stuff coming in the either next class or the class after for us to practice these rules on, because like this is stuff we want to be fast at and get good at recognizing, like what kind of tricky crap can Mr. Kulik pull to try to hide, obfuscate how to do this with this rule by adding some algebra layers on top of it. But this is the start of like, life's about to get a whole lot easier and these limits are basically gonna go bye-bye outside of, proving something. So like, we've turned the corner and the limits are now gonna be in the rear view mirror for all of you that are like, get them limits, I hate this stuff. it's gonna start looking a whole lot more mathy, because we're gonna be symbol pushing a bunch and like solving equations, like finding where the derivative is equal to whatever. It'll start resembling again what mathematics felt like. And then we can turn the corner into applications of this stuff, and it's like, oh, then it all goes away again. What do you guys think for today? Was this felt pretty good? What a relief this is, though, to get rid of the limits definition. Like, now I can do this in one line instead of one page. Yes, sir.
I have some questions on the direction.
Okay. Yeah, you can ask.
For 3B, it says show that as continuous, but we did it, but it wasn't.
Let's see. Yeah. So I would just say that result would just be like.
I didn't start it.
Other. So here I would say, well, then it's just continuous from what is here. So if it doesn't work, I'm gonna explain why, and that's fine. So that is a type of
Yeah.
it's not working. Like telling me it's different. Just say it's not.
Can we ask you during here? I just followed the one I did not even know that it was. I don't think it's usually. Yeah,
Let me just, so you're checking.
I know. Yeah, it's good.
So,
Is it on
what
the?
you've done here, this is.
Right, so you say.
No, this
Wait,
one-
what's time? It's 22. Yeah, she's a lot.
These limits are zero.
Anyway, not there. Yeah, exactly. Not do it.
No, this is like -1. The other one is 0.
Yes.
So I think that what you've done here looks good.
I'm gonna ask.
I would change it to exactly what you should. I would change it to exactly what you
Because I
should.
really don't want to do that.
That looks good.
Yeah, I even just read the information.
Okay. So if I look at these three functions, which one's up? So I'd say that's the sin x.
But it would take.
Oh, I did that last semester.
Wait, I just see Ellie's homework. You see Ellie's post there. It's so funny.
Okay. So that's how I started there. Does that make sense? And you're trying to get into this thing.
So, I got confused.
Yeah, I know.
So I would, so here I would, so you're stuck here, and that's on the wrong spot, right? And this gets to be in the middle. So what I would do is say,
Yeah.
I would try to get, well, I can't get this, right? You get this.
I was thinking about it.
You're so behind.
I know.
2 more years of this.
And then if you take the reciprocal of everything.
But it's a surprise, so don't. Because I do
That's tricky, right? Hi. Okay, so if I look at the graph, so what function is on the bottom?
Yeah, it was like,
So I start finding all the
you
signs.
got to the factor eight.
Like, you don't know the vision. I know.
What's the graph? Go.
No, I
know.
But it says
That's what you want the middle term to turn into sin x. That's what you're trying to build out. That's like all sides of the
I know.
Well, then you'll take
I know. I'm like,
Whoa.
Yeah,
Yes, the other one here is a little
oh my god, stop saying that,
Think
because I
about it.
forget
Come
about it.
back,
Oh,
you
my
haven't tried
goodness,
this
like,
before.
yeah,
Come back.
I don't know.
I'll see what you looking for.
But let me just start out. Oh, should I type this in?
If you're done, I'll take it.
Okay, thank you.
Sure thing.
I'm done.
So I just said that.
I'm just do like as everything happens, like that's where
I'm
I.
actually excited for a guys.
Now.
Smile. So we're